Okay, in this video we're going to use algebra a little bit creatively. If you never thought of algebra as a creative kind of a medium like painting or sculpture or something like that, what we're going to do is use what we know about algebra and try and invent a formula that will generate Pythagorean triples. Okay, what we're looking for are, if I take two whole numbers, like say A, and I square it, and I take B and I square it and add them together, I want this to come out a perfect square. Okay. Now there's no rules to this game. How do we hunt for this formula? But basically mathematicians take things like this and they start exploring and trying things. And one thing, it turns out, leads to a little bit of progress. If I subtract a squared on both sides, instead of trying to add these, let's look at subtracting these, and I'll show you why. I'm going to take c squared minus a squared and see if I can find some way to force this to give perfect squares as a result. And the reason I picked this form is because that's the difference of two squares, and we know how to write this differently. If you have had Algebra 1 and remember the difference of two squares formula, you can write this as c plus a times c minus a. If you just multiply this back out, you'll see the middle term cancels and you get this expression. If you haven't had Algebra 1 this far, or haven't gotten to this part of Algebra 1, the rest of this is probably not going to make much sense to you, so you might want to skip over this video, come back to it later. Okay. Let's proceed, assuming that you understood what I just did here. Okay. So let's see what we have. I have two squares of whole numbers, and I want to somehow force this to be a perfect square of a whole number. Well, one thing I could do is force each of these to be perfect squares. So if I say that I want c plus a to be some number squared, and I want c minus a to be some other number squared, let's see if when I choose any two numbers, m and n, m squared and n squared will be perfect squares. Can I figure out corresponding values of c and a? Well, watch this. If I take c plus a and set that equal to m squared, and c minus a and set that equal to n squared, so 2 there. Okay. Notice I have two equations and I can solve for both c and a. When you have two equations, you can solve for two unknowns, right? If I add the two equations together, a drops out because there's a plus a and a minus a. So I'll have 2c, and if I add these, I have m squared plus n squared. Or I could do something different. If I took these equations and subtract c minus c, the c would drop out. A minus a is a plus a, which is 2a, and this minus this is m squared minus n squared. Okay, and if I take this and divide by 2, and I take this and divide by 2, I now have a formula for a and c, so that if I choose any two numbers m and n, I can come up with a corresponding value for a and c that we could plug into this formula up here and make it work. Okay, I could actually stop right here and just do exactly what I just said, or I could go ahead and plug these in. Let's do that. So we'll solve it algebraically. It'll make evaluating the numbers a little bit easier. So what I want to do is take every occurrence of the c and put this in its place. So I have c squared, so I write this as m squared plus n squared over 2. That's right here, that's the c. And when I square it, I'm going to square both top and bottom. That's equivalent to squaring a fraction. If I multiply two fractions together, you multiply the tops together and you multiply the bottoms together. Remember that? So that's c squared. And then a squared, subtract a squared here. Well, here's a, m squared minus n squared over 2. And if I square that, I'll square the top and square the bottom. Is equal to And this expression here, the whole c plus a, is simply m squared. And this whole expression is simply n squared. Okay. Now, let's clean this up a bit. This is a 4. And this is a 4. So let's multiply through by 4. So we'll have m squared plus n squared squared. And this is m squared minus n squared squared is equal to 4m squared n squared. But notice this is simply 2mn squared. Aha! So if we pick two numbers, m and n, and you plug them in like this, so I calculate a value here, and a value here, and 2mn here, we're guaranteed that this number squared minus this number squared equals this number squared. That means this one's going to be the hypotenuse, because remember we took if you take the hypotenuse squared minus one of the legs squared, you get the other leg squared. And so that's what this would give us. Okay, let's look at a couple examples like this. Okay, here I've written down those three formulas, and so the hypotenuse is the one where we have m squared plus n squared. So let's do this by hand. If m is equal to 2 and n is equal to 1, let's see what we get. Now I chose m to be the larger of the two because in the second equation here, notice we have m squared minus n squared. If this were smaller than that, this would come out negative. We want to keep all these positive, so we want to insist that m be greater than n. So that's another condition we're adding to this. Okay, the others, there's no problem. So m is greater than n. So let's see what we get. This first number is 2 squared plus 1 squared. Well, 2 squared plus 1 squared is 4 plus 1 is 5. How about this leg? This is 2 squared minus 2 squared minus 1 squared. 2 squared minus 1 squared would be 2 squared is 4, minus 1 is 3. And 2mn is 2 times 2 times 1, which is 2 times 2 times 1 is simply 4. There's our 3, 4, 5 triangle. Okay, let's try this with another pair of numbers. Let's let m equal 3 and n equal 2. Let's see what we get. Well, 3 squared is 9, and 2 squared is 4. 9 and 4 is 13. So we get 13 here. This leg is, this would be 3 squared is 9, minus 2 squared is 4. Well, 9 minus 4 is 5. And here's 2mn. Well, mn is 3 times 2 is 6, times 2 is 12. So 2mn is going to be 12. And there's our next one, 5, 12, 13, is another Pythagorean triple. We're batting 1,000 here, as they say. Let's do this systematically now, and we can do this. We can put this formula, these formulas, into a spreadsheet and generate these Pythagorean triples directly, instead of just having to hunt everything and calculate everything out and try it. We can go directly to these Pythagorean triples. Okay, I've set up the spreadsheet ahead of time with these columns. I'm going to systematically cycle through all pairs of m's and n's, requiring that m be greater than n. And then based on these selections, I'll compute the three numbers of our triple, as we've seen before. And I also included a test. If these were done correctly, the sum of the squares for these two columns should equal the square of this column. And so I'll just do that here to make sure that we got good triples. All right. So the tricky part is going to be cycling these in such a way that m is always greater than n. So let's do the first few by hand, and from that let's see if we can come up with a pattern. All right. So I'm going to start with a 2 here and a 1 here. That was one of them that we did by hand a few minutes ago. All right. Now let's go ahead and compute the formulas over here based on these. So this one, it says 2mn. So I say equals 2 times m, which is that, times n, which is that. Okay. This one it said b is equal to m squared minus n squared. So I'm going to say equals this squared minus this squared. And this one is m squared plus n squared. And so I'm going to say equals this squared plus this squared. Okay. And I have my 3, 4, 5 triangle there. The test over here is this one. I want to make sure that the sum of these two squares equals this square. So the test here is the sum of the two on the left. So I'll say equals this squared plus this squared, which is 25 as we expected. This is equal to this number squared, which is also 25. That shows that this is a correct Pythagorean triple. Okay. Now, how do you get these m's and n's to work out the way we want? Let's do the first few by hand and watch for patterns here. So after 2 and 1, that's the only one where I can have m equals 2, because there's only one value smaller than 2 for the positive whole numbers. So let's go to 3, and I have two possibilities here. I could put a 2 or 3 followed by a 1. Let's do one more set by hand. So this could be a 4, this could be a 3, 4, 2, 4, 1, and then we're going to make a transition again. Okay, so looking at the pattern, what we have is that each time, unless this number hits 1, it's going to be the case that we're going to repeat the m, keep repeating the m until this hits 1. In this column, we're going to simply let the number get 1 smaller each time until this hits 1. Okay. So let's see if we can formulate a formula here that will do that. So this one I'm going to say equals, and now I'm going to start with an if. So if this number here is greater than 1, which it's not in this particular case, but that in these other cases it might be. If this number is greater than 1, comma, we're going to have this cell simply be equal to the previous value, comma. Otherwise, if it hits 1, I want to bump it up 1. So I want it to be equal to the previous value plus 1. And then close the parentheses. So notice it was a 1 here, and so it bumped it up 1. All right, what about here? Start with an equal sign. If the previous value here is greater than 1, what do we want it to be? Well, we want it to be 1 less than the previous value, because it's going to go 3, 2, 1, then 4, 3, 2, 1, and so forth. So this would be equal to that minus 1. But if it hits 1, we want it to be equal to this number over here, minus 1. We want it to start 1 less than. So like when it was 3, we want to start with a 2. When it's a 4, we want to start with a 3, and so forth. And let's try that. This minus 1. Close it. Whoops, something went wrong. Notice this should be a 4. Let's look at it for a minute. What we want it to be is this is 1 less than this value, which is the number in A8. Over here we had A7. Let's just change that manually to A8. That wasn't visible when we were doing the formula, so that was misleading. All right, now we got a 4. So it's A8 minus 1 is this value minus 1. Okay, let's see what happens if I propagate this formula on down. Here we go. So this is 2 and 3, 3 and 4, 4, 4 and 5, 5, 5, 5. And in the meantime over here, 5, 4, 5, 3, 5, 2, 5, 1. Then it goes to 6, 5, 6, 4, 6, 3, 6, 2, 6, 1, 7, 6, 7, 5, 7, 4, 7, 3, 7, 2, 7, 1, etc. This next one should be 8, 7, and there it is. Okay? These formulas we've already put in there based on the values over here to the left, so they should still be good. So if I select all of these formulas and propagate them on down, there we have it. All right, we have ourselves a bunch of Pythagorean triples here. On this side, we just have verification. Notice that all these pairs of numbers are equal, which says every single triplet that we've generated here is valid. And since we could keep this going forever, there's no limitation on how high the m's and n's can get, one of the conclusions is there are an infinite number of Pythagorean triples that we can generate. Okay, notice that we can recognize some of these triplets from what we've experienced just recently. Here's our 3, 4, 5. This next one is 5, 12, 13. Okay, this next one is 6, 8, 10. That's one that we said is not a primitive one. It's a doubling of the 3, 4, 5. Okay, so we know just from this example here that this list does not limit itself to only primitives, but it has multiples of some of the primitives included. On the other hand, we can easily see, as I'll show you in a second, that not all of the multiples are included. Because look at this. Here's 3, 4, 5. If I double it, I get 6, 8, 10. But if I triple it, I'm looking for a 9 and a 12 and a 15. And notice there are no 15s in this column. Okay, so there's no 9, 12, 15. Here's a 15, but it's the wrong pattern. It's an 8, 15, 17. Okay, so not all of the multiples are included. However, and this I'm just going to tell you, and you can take it on faith or go study a lot more. This set of formulas here has been studied extensively by mathematicians, and it has certain interesting properties. It turns out the list that you generate is guaranteed to include every primitive Pythagorean triple. It also includes some, but not all, of the multiples of these primitives. Now, if you want a little bit more information, it turns out that, again, this is from extensive study, and I'm not going to go into proving this here. I'm just going to drop it in because it's sort of interesting. Some of the restrictions on the m's and the n's. If you want to guarantee that what you have here is a primitive triple, it turns out you need to guarantee that the m and the n, first of all, must be relatively prime. In other words, think of it like it can't be something that could be reduced like a fraction. Like down here, look at the 6 and the 3. That could be reduced because they have a common factor, namely 3. And notice over here, the 36, 27, and 45, 3 is a divisor of all of these. In fact, 9 is a divisor of all of these. So you could reduce this, and so this is not primitive. Okay. Secondly, it turns out that if m and n are both even, or if they're both odd, then these will not be primitive. So let's find some examples like that. So what we want to find is one odd and one even, and that's how we find our primitives. So here's an even and an odd, and we have 3, 4, 5, no problem. Here's an odd and an even, 5, 12, 13, no problem. But look at this one, 3 and 1, that's both odd, and this is not primitive. This is a multiple of the 3, 4, 5. Okay. What about this one? 4 and 3, that's an odd and an even. This is primitive. 4 and 2, they're both even. This one is not, and so forth. What do we know? Every single one of these is a Pythagorean triple, and we've tested that part out, and we have all the primitives. So that's two pretty strong conditions there. We have some extra clutter, but that's just because, hey, we're doing this at a fairly introductory level. So there you have it. Here is a cleaner approach to finding Pythagorean triples. We've seen a brute force technique where we just test everything, and here's a formula that will lead us to a list. And so that's pretty cool.